I guess someone in this class would want me to say, and we're live! So we are. Folks, we're going to be looking at radioactivity. It's a little weird, I know, hearing this disembodied voice coming from the speakers, but that's okay. We're going to start part of the lesson, and then I'm going to try and give you as much class time as I can for you to finish up the homework so you have no homework for the Christmas break. But it's a big, long topic, so I wanted to get a head start on it. And it's a cool topic. We're going to be looking at radioactivity. So, section 7.1, radioactivity. Radioactivity is the release of high energy, running out of room, particles. Radioactivity is the release of high energy particles or rays of energy as the result of the nucleus of an atom breaking down. Some atoms have an unstable nucleus. Not all. In fact, only some forms of some atoms are radioactive. Mostly towards the bottom of the periodic table, but some a little higher up too. Examples, uranium is radioactive. You may have known that. You may have heard of uranium. Radium is radioactive. Now both of those are towards the bottom of the table. Potassium is radioactive. That's higher up on the periodic table. Oh, by the way, you might want to get out your periodic table, your pink sheet. So I'm going to pause for 30 seconds here while you get out your periodic table, your pink sheet. So get out your periodic table. Oh, that's 30 minutes, way too much. Hurry up. Get it out. Hurry up. Get it out. 20 more seconds. Oh no. This giant clock is counting down. What will I do? 10 more seconds? Well, 12 more seconds. 9, 8, 7, 6. Do you want to count with me? 5, 4, 3, 2, 1. Here comes a noise. Okay, there you go. Got your periodic table out? So uranium and radium, they're far down on the periodic table. In fact, uranium's kind of like along the bottom row there. Potassium isn't. There's also something called background radiation. Background radiation is all around us. It's everywhere. And it's harmless. But it's very difficult to detect. In fact, scientists use a Geiger-Muller counter, or a Geiger counter for short, to measure it directly. This is a little device that makes a clicking noise every time it detects some kind of radioactive particle. More clicks, faster clicks, more radiation. So we said that radioactivity is the release of a high energy particle or a ray of energy from the nucleus breaking down. It might be worth drawing a picture of a nucleus. I'm going to cheat. Here's my atom. Yoink. Right there. Kind of round, kind of not. Here's what I want you to realize. We have inside the nucleus particles called protons. We have inside the nucleus particles called neutrons. Close my browser so it's out of the way. And in shells around the nucleus, we have, yes, you guessed it, electrons. So when we're talking about radioactivity, we're talking about protons and neutrons doing weird stuff, the nucleus. So remember, the nucleus contains protons and neutrons. And electrons are in the outer shells. Certain types of radiation, two main types. Energy radiation and particle radiation. Energy radiation is gamma waves. Hulk say gamma wave! No, yes, I know it's what, according to the Marvel Comics, turned the Incredible Hulk into the Incredible Hulk, gamma rays. Well, they do some damage. By the way, the symbol for gamma, if you draw a little fish like that, but you turn it on its head like that, that's the symbol for gamma. Looks like this. Gamma waves. Gamma waves are part of the electromagnetic spectrum. The electromagnetic spectrum is the radiation that's all electromagnetic spectrum is the radiation that's all around us. You are all right now surrounded by types of energy radiation. Most of it is invisible. Your eyes can only see this small section right in here. Wavelengths of about 10 to the negative 6 meters long. There's radio waves, which your eyes can't see. There's microwaves, which your eyes can't see. Microwaves are about 10 to the negative 2 meters long. That's about 1 centimeter. There's infrared waves, which are pretty short. Then there's visible light. We can see these colors right in this section here, very small section. Then there's ultraviolet light, which we can no longer see. Then there's X-rays, which doctors use, and then over here there's gamma rays. They have a very, very, very short frequency, 10 to the negative 12. That means that they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1 meters long. They're really short. Gamma rays. Hulk likes gamma rays. Oh, shut up, Hulk. Then there's also particles. There are two main particles that are emitted as radiation. So we have gamma waves, gamma rays, and we have alpha and beta particles. The symbol for alpha looks like that. It's a little fish on its side. It's where we get our lowercase letter a from. And the symbol for beta looks like this. It's like a capital B with a long drooping tail. And yes, it's where we get our capital B from. In fact, the word alpha, beta is where the word alphabet comes from. It literally means A's and B's, ABCs. And this is emitted by the decay of some atoms. We're going to talk about where and when each of these show up. When gamma rays are emitted and when alpha and beta rays, particles, are emitted. First, we need to talk about isotopes. Isotopes. Isotopes are more than just Springfield's football team, if you watch The Simpsons. Different atoms of the same element can have different numbers of neutrons. If you're part of the same element, you have to have the same number of protons because the number of protons is what defines what element you are. If you have 16 protons, you're oxygen. But you may not all have the same number of neutrons. Some elements always have the same number of neutrons unless we muck around with them. But there are some elements naturally occurring that are radioactive, and we say when they have different neutrons, that means that they have different masses. This helps explain why, when you look at your periodic table, all those atomic masses, so many of them have long decimals. They aren't evenly worked out whole numbers. It's because the atomic mass on your periodic table is actually the proportional average of the most common radioactive isotopes. And that's going to be our word. Atoms with the same number of protons, but different numbers of neutrons are called, here's your word of the day, I'll do it in red, isotopes. And then I wrote here, see table 7.1 in your textbook. I'll bring that up in just a second. So here is how we write an isotope. We write that, and that. Say what? Where X is the element symbol. If I'm going to write, for example, radioactive potassium, boom, K for potassium. A is the atomic mass, and this changes depending on the isotope we're looking at, depending on the number of neutrons that are kicking around. Z is the atomic number, and it's also the number of protons. Z is the atomic number. It's also the number of protons. Let's look at an example. Uranium, radioactive. There are many types of uranium. There's uranium-235. There's uranium-238. There are other kinds as well. You'll notice uranium is what element number? Find it on your periodic table. It's in the bottom row. You'll see it there. It's element 92. That means it has 92 protons. So no matter what radioactive element we're talking about, if it's uranium, it's got 92 protons. It's the isotope which changes. That's the number of neutrons. What changes? The atomic mass. This has an atomic mass of 235. This has an atomic mass of 238. This has an atomic mass of 235. This has an atomic mass of 238. Z is the atomic number, 92. 92. It's also the number of protons. But remember, the number of neutrons was take the mass, subtract the number of protons, the atomic number. That's how many neutrons uranium-235 has. It has 143. How many neutrons does uranium-238 have? Well, it has a mass of 238 atomic mass units minus 92 protons. It's got 146 neutrons. It's got some extra neutrons in its nucleus. And that makes neat radioactivity things happen. For example, there are three main isotopes of potassium. There's potassium-39, potassium-40, potassium-41. All of them have 19 protons in the nucleus. Why? Because potassium is element number 19. Oh, and because they're neutrally charged, they also all have 19 electrons. Same number of protons as electrons, because they're not ions. But they're isotopes. Potassium-39 has a mass of 39. It's got 19 protons. If I subtract 39, take away 19, I find that potassium-39 has 20 neutrons. It would be written as potassium-39, 19. And we would say that as potassium-39. Potassium-40, that's got a mass of 40. It's got 19 protons. If I subtract the atomic mass from the number of protons, I find that it has 21 neutrons. We would write that still as potassium. We would write that still as element number 19, but it has a mass of 40. You'll notice the number of neutrons don't appear in the actual formula. We've got to calculate them. Hey, how many neutrons will potassium-41 have? Well, potassium, again, has an atomic number of 19. That means it's got 19 protons. It has an atomic mass of 41. 41, take away 19. You may need your calculator, or you can do it in your head, but I'm pretty sure it's got 22 neutrons. And I would write it as potassium-41. If you turn to page 290 in your textbook, you can see the potassium breakdown in a typical banana. If you've eaten a banana, you have eaten all three of these types of potassium. Yes, you have eaten some radioactive isotopes. The potassium breakdown on a typical banana, it's mostly potassium 39. That's by far the most common element. 93.26% of potassium is that. 6.73% is potassium 41, and 0.01% is potassium 40. Almost none, but it's there. And no matter which banana you try, you would find the potassium in roughly those same proportions, very close to those same proportions. So in another banana or a totally different source of potassium, the percentage composition of potassium isotopes will still be about the same. So then we get to radioactive decay. So some atoms are radioactive. Which ones? Atoms are only radioactive if their nucleus is unstable. It's difficult to predict which, if any, isotope of an element will be radioactive. You'll get a table in your data package. I'll photocopy that. It'll be photocopied on color paper, like your pink sheet, like your yellow sheet. I'll give it to you after New Year's, after the school Christmas break is over. Isotopes that are unstable and therefore able to decay are called radioisotopes. And when these unstable atoms emit particles and or energy, gamma rays, energy, particles, alpha and beta particles, they are said to have undergone radioactive decay. As an example, uranium-238. So uranium-238, it's got an atomic mass of 238. Uranium is element number, what? 92, by the way. So if I'm bored, I can go 238, take away 92. It starts out with 238, take away 92, 146 different neutrons in its nucleus, and it goes through a fairly lengthy decay process. The first thing that it does is it gives off an alpha particle, and when it does that, when it gives off an alpha particle, it turns into TH, which is thorium. Thorium-234. And you'll notice thorium is really close to uranium on the periodic table. It's element number 90. Thorium gives off a beta particle and turns into Pa. What's Pa? Protactinium, element number 91. Protactinium gives off a beta particle, turns into uranium, but not uranium-238, uranium-234. But that's not stable either. It gives off an alpha particle, it turns back into thorium, but this time thorium-230, which is also unstable. It gives off an alpha particle, it turns into radium-226, which is also not stable. Now what? Well, radium gives off an alpha particle, and it becomes Rn. What's Rn? That's on your periodic table. It is element number, I'm looking for it right now. Oh, radon, element number 86. But it's an isotope. It's radon-222, which is not stable. It's going to give off an alpha particle, and it's going to turn into PO. What's PO on polonium, element 84, polonium-218. Still not stable. It's going to give off an alpha particle and turn into Pb. What's Pb? Lead. Lead-214, but this is radioactive lead. It's going to give off a beta particle, because blue means beta. When it does that, it's going to move up on the periodic table. It's going to become bismuth-83. bismuth 214, element 83. Bismuth is radioactive. It's going to give off a beta particle and become PO. PO is polonium. It's element number 84. This is polonium 214. Polonium, radioactive, gives off a beta particle, becomes lead, gives off an alpha particle, becomes lead, gives off a beta particle, becomes bismuth again, gives off another beta particle, becomes polonium, and finally, after a long time, how long? Years and years, a long time, you end up with a stable isotope of lead. Lead 206. Now the lead is happy. 14 different decay steps going on. It's one of the reasons we use uranium in nuclear reactors and nuclear bombs. It's radioactive. It's very willing to give off neutrons. Here are some isotopes of carbon. You have carbon-12, which is almost all the carbon. It's most of the carbon in you. It's stable. There's also carbon-13, has a mass of 13, 6 protons, but it's got 7 neutrons, 1 extra neutrons. It makes up 1.1% of the carbons on the planet, and it's stable. But 1 atom in 1 trillion atoms, very few, is carbon-14. Carbon-14 has an atomic mass of 14. Still has 6 protons, because that's what makes it carbon. But it's got 8 neutrons, and that extra neutron makes it unstable. It wants to enter a stage of radioactive decay. What are some common isotopes, parents and daughters? Carbon-14 wants to decay into nitrogen-14. It takes 5,750 years for half of it to change into nitrogen. We call that the half-life. So if you had 1 kilogram of carbon-14, after 5,730 years, you'd have half a kilogram, and the other half would be nitrogen-14. Go another 5,730 years, and you'd have 25%, 0.25 of a kilogram. Everything else would be nitrogen. Uranium, as I said, takes a long time to become lead, 710 million years. Oh, and that's uranium-235 to lead-207. Going back to this chart, that's uranium-235. I don't even have that on this chart. And that was to lead, lead-207. I don't even think I don't have lead-207 on this chart. The one we looked at was uranium-238. Hey, uranium-238 to turn into lead-206, as I said, it takes a while, 4.5 billion years, about the lifetime of the Earth. Potassium-40 decays into argon-40, takes 1.3 billion years. This one we only figured out recently. Rubidium-87 takes 47 billion years to become strontium-87. We thought for the longest time that rubidium was stable. So we looked at isotopes. We're going to pause here. When we come back, we're going to pick up where we left off with 3 types of radiation. What's your homework? You got some room. You can write the homework right here underneath where it says atomic mass number. First of all, you can go from the textbook, page 291, practice problems. You can do number 1, 2, 3, and 4. So you can copy the chart out in your book, filling in the atomic number, the number of neutrons, the atomic mass number. Number 2 is asking you to analyze the library. Remember, the answers are on page 592 if you get stuck, or you can ask for help. If you finish that, you can hand it in, or you can hand it in after the break. And the second assignment is the isotopes sheet. That's the one that's going to be handed out right now. It's called Isotopes Homework. It's asking you to fill in some definitions. Then on the back, you're filling in a chart. And I have attached answers if you get stuck. If you finish all that, hey, you have no homework for the Christmas break. Okay? When we come back, we will look at radioactive decay and radioactive particles. I will be coming in over the Christmas break, and I will email you your test scores, so you will find out what you got. That'll be my Christmas present to you. I hope you all did really, really well and found it okay. Probably a little tougher than the acids-bases test, but I think you guys were really well prepared. I hope you did awesome. Have a Happy New Year. Have a very Merry Christmas. Oop.